It all begins with an unimaginably cold cloud. This cloud contains the seeds of whole new worlds, stars and planets about to be born. Molecules of hydrogen and helium gas, which normally zip around at high speeds, slow down and clump together because of gravity. Tiny grains of silicates, iron and carbon-rich material, together classified simply as dust, send some of the gas's energy back out into space, making the cloud even colder. The dust grains spiral into the central knot of matter, like water running down a drain. As this pocket of the cloud contracts and thickens, a bright, hot ball begins to form at the center as more gas and dust are pulled in. Gravity is waging a battle against the pressure of gas and magnetic fields, and gravity is winning. While the infant star takes shape, the material spiraling inward flattens into a pancake-like structure known as an accretion disk. Why does this happen? The gravitational tugs of the galaxy's billions of stars may have accelerated and shocked the gas. Or, maybe two clouds are bumping into each other, causing pockets of gas to coalesce. But sometimes, the catastrophic explosion of a massive star drives strong winds of material into a star-forming cloud, a death resulting in a new birth. Now that we have our stars, how will they get to have planets orbiting them? The newborn star is a feisty baby, shooting out violent jets of magnetically accelerated material as it gets nourishment from the gas and dust whirling around it. Like a blob of pizza dough flattening out as the chef spins it, this material condenses into a flat disk. That dough has a preferred direction inherited from the collapse of the cloud. That same spin will remain with the system for its entire life, unless another star system gets close enough to interact with it. At about 100,000 years, the cloud starts to thin out enough to reveal two distinct structures, a newborn star and a fluffy, diffuse disk of gas and dust. A very young disk around a star contains mostly gas with dust, no bigger than grains of sand, swirling around in it. The baby star is still throwing out extremely hot winds, dominated by positively charged particles called protons and neutral helium atoms. A lot of the material from the disk is still falling on the star, but small groups of lucky dust particles are crashing into one another, clumping into larger objects. Planets will form from less than 1% of the mass of the disk. We look at our solar system now, and we're just seeing the stuff that has survived that initial process, Momajek said. There might have been earlier generations of planets that actually migrated in and were absorbed by the Sun, in just the first few million years of our history. The presence of gas helps particles of solid material stick together. Dust clumps become pebbles, pebbles become larger rocks that grind together to enlarge. Some break apart, but others hold on. These are the building blocks of planets, sometimes called planetesimals. Based on just an image of baby planets in a protoplanetary disk, it is impossible to determine what the system will look like as it matures. Is disk destiny? Probably not, said Heather Knutson, professor at Caltech in Pasadena. Growing planets don't stay put. They move around. They interact with each other, and with the gas disk, in a way that can be quite random and messy. But nothing stays young forever. Every planetary system eventually hits middle age, just like our own. At approximately 100 million to 1 billion years old, planets tend to settle down in their orbits and stars don't flare up as much. Our own solar system, about 4.5 billion years old, is the model for this idea of planetary middle age. Mandel thinks of our planetary system as about 45 to 50 years old, when scaled down to a human lifetime. But by studying exoplanets, The planets beyond our solar system. Scientists know that our solar system is not the only way a planetary system can look in this comfortable age of life. At the age of our solar system, things are calm, for now. But as a star gets older, it may end up obliterating some of its planets. Will Earth survive? When our Sun approaches its red giant phase some 6 billion years from now, it will run out of fuel in its core. As hydrogen fusion slows, the core once again begins to contract. As the core gets smaller, it heats up until can kick off another round of nuclear reactions, fusing helium into heavier elements such as carbon, nitrogen, and oxygen. The hotter core also makes hydrogen fuse in the shell of material surrounding the core. Meanwhile, extra heat produced deep within in the star causes its outer layer of gas to puff up. The end of the red giant phase is typically the most violent time in a star's life. The bloated, dying star throws out material from its outer layers in intense episodic bursts. In our own solar system, the Sun will puff up so much that it will melt, evaporate and eat up some of the inner rocky planets. I am confident that the Sun will swallow Mercury and Venus, and not Mars. But the fate of the Earth, which resides in between, is less clear, said astronomer Dimitri Veras at the University of Warwick. Scientists studying whether or not Earth will be both toasted and swallowed create computer models of the gravitational interactions between Earth and the Sun as the solar system ages. Recent modeling suggests Earth probably won't make it out intact. But even if it does, all of the planets that survive will experience skyrocketing levels of energy from the expanding Sun, bathing their atmospheres and surfaces with intense radiation. We'll all be long gone, Mandel assured us. Earth won't be habitable, and the only chance for survival would be for an advanced civilization to migrate to a new planetary home. The planet's orbits may also become unstable. As the red giant loses mass, the star's gravitational hold on its planets becomes much weaker, so their orbits will expand. In our own solar system, the Sun will throw off about half its mass, so the outer planets' orbits will drift outward, settling twice as far as they are today. Neptune, at 30 times the Earth-Sun distance, will eventually hike out to about 60 times the Earth-Sun distance. Approaching the end of its fuel-burning life, the Sun will become much brighter and bigger. It will grow so large in diameter that it could fill the entire sky from the surface of a surviving planet. Will the Sun and stars like it die in a fiery explosion or collapse in a small whimper? Check out to find out. When the core of the former red giant has exhausted all of its fuel and shed all the gas it can, the remaining dense stellar cinder is called a white dwarf. The white dwarf is considered dead because atoms inside of it no longer fuse to give the star energy. But it still shines because it is so hot. Eventually, it will cool off and fade from view. Our Sun will reach this death about 8 billion years from now. Observations of dusty debris belts around white dwarfs suggest that giant planets may hold small bodies in orbit around a white dwarf, and even fling them inward, to be chewed up by the dead star. This idea took root because of a variety of heavy elements detected in the atmospheres of white dwarfs, so heavy that they should have sunk into the dense, dead star long ago. Almost every star in the universe eventually goes through this transition from red giant to white dwarf, although extremely low-mass stars will take longer than the present age of the universe to get there. However, if a star is extremely massive, it could follow a different path, expanding into a supergiant star and ultimately exploding as a supernova.